All right. So picking up where we left off last time, we were talking about the evolution of our languages, right? So we talked about the evolution of C into C++, which is really the transition from um, procedural languages into object-oriented languages. And we talked about that kind of being like a piece of Tupperware, just an organizational tool that we have. So we looked at an example of a struct in C, which was a tool we had in C for representing a collection of pieces of information that aren't necessarily of the exact same type. So for instance, here's a struct called person that can store a person's first name, a last name, their age, and we can assume a first name is a different kind of value than a person's age. Age is a number, their name is like a string, something or other. But we had some weaknesses with structs in that they couldn't also contain functions. They couldn't retain reusable chunks of code. So when we went to C++, they allowed us to put more stuff into a container, and it gave us the ability to hold something called a class. Now, create something called a class, which is a lot like a struct, with the exception that now we can take a function like display, and we can put that guy inside of the class, where we were not allowed to do that with structs. So now we have a container that can hold some other things, other kinds of things, which is, let's say, better. All right. But it's not always the right tool for the job. Sometimes we don't need to store functions and that kind of stuff. So it's not always a better solution, but it does give us some flexibility when we need it. We talked about this thing called the pointer, which is just a variable capable of holding a memory address. So memory addresses tend to be a little bit intimidating. I think I asked the question last time, was which scares you more, the number 5 or this crazy thing? For most of us, this crazy, I mean, you might not be necessarily terrified of either, but, this crazy thing looks a little bit more intimidating than just the number 5, because we're used to dealing with these, where memory addresses in our computers are foreign to us, right? Yet we deal with addresses in real life all the time. You have your home address, and we put it into Amazon all the time like it's no big deal. And those are actually more complex than our addresses inside of our computer, because the way our computer works, and you'll learn about this in the 325 class, Computer Architecture and Organization, is our computer memory is like one gigantic street, all right, with a billion houses on it. And this is house 0, this is house 1, this is house 2, this is house 3. So this guy ultimately translates into a really, really, really giant number. Well, potentially a giant number, okay, that we're representing in base 16 rather than in base 10, like we're used to, right? Now, out of curiosity, how many of you have ever done base conversion, like converting from base 10 to base 16 to base 2, those things? What's up?
Like just for fun?
Well, yeah, I mean, you don't sit around and just do that stuff for fun? It's like, I bet you it would be really creepy just to do everything in binary today. Like, how old are you? And you convert your age to binary and all right, so let's actually look at that for a few minutes just to kind of gain an appreciation for these memory addresses. Now, one hint here would be I am a huge, huge, huge fan of conversion problems. So there's a high likelihood that at some point you'll have a quiz to convert some stuff, and every exam I ever give has at least one conversion question on it. It doesn't even matter what the subject is. Every class you will ever have with me, every exam will have a conversion question on it. Because we can't have seniors who don't know how to convert a binary number into a decimal value and vice versa. Those are kind of important things. Okay? So let's start with, now one thing I like doing with this, and it's kind of a misunderstanding, so most of you in here haven't done number conversion stuff before, right? Because we never had to. Most of us, we got 10 fingers, 10 toes, base 10 kind of works for us, right? Somewhere in first or second grade, we kind of got pretty decent at doing some mathy stuff and counting and all that crap, and it's kind of worked well for us up to this point. Well, now when we start dealing with computers, the binary stuff, zeros and ones, is going to be useful for us sometimes. The hexadecimal stuff, the base base 16 is helpful for us sometimes, and I'll kind of circle back on that here in a few minutes. But if we talk about conversion, one misunderstanding that often happens is that you think you have to memorize how do you convert a binary number to a decimal number. And then you have to memorize how do you convert an octal number to a decimal number. Like those are two completely different things. The process is identical no matter what base you're starting from and what base you're going to. The only thing you change is the number you're either multiplying by or dividing by. That's it. For base 2, you're multiplying or dividing by 2, depending on which direction you're going. For base 8, you're multiplying or dividing by 8, depending on which direction you're going. For base 16, it's by 16. So if I said convert something from base 10 into base 24, which doesn't really have a name, you can do it. You're just multiplying or dividing by 24 instead of something else. So let's look at a couple of these guys so we have an appreciation for what these conversions kind of mean, and that'll hopefully demystify this idea of a memory address a little bit so we can kind of understand that all this guy is a number. This says go to house 6,204. That's all that crazy looking number actually means. All right. So we usually start off. So let's start off. Like I said, I had a birthday last Friday, so it was my 21st. So if I want to convert 21 from decimal, base 10, so decimal's base 10, into base 2, I have to divide 21 multiple times and then record the remainder. How many of you have had third grade math? Hopefully all of us, right? Okay, remember long division? We loved long division, right? You would come up with some answer, and then you have a little r, and then another number, right? What was that r? What did that stand for? The remainder. Okay. Now, when we became older, we no longer deal with the remainder crap, right? Now it's always something point something. We use, numbers with decimal points after it. Okay. Well, now we come back to our computer science education. We realize, you know what? Those remainders are actually pretty important. So converting numbers is actually based on something you learned in third grade. I think that is when they still do long division, right? Third grade? Or is it like first grade or something now? When I was a kid, it was in third grade. But now it's possible you're doing calculus as a second grader. I don't know. I don't know what they're doing these days. Okay. So when we want to go from decimal to some other base, so conversion from decimal to another base. What we're going to do is we're going to divide over and over again until we finally get a quotient of, quotient of 0. Okay, and I'll show you this as an example here in a second. So we're going to go from the decimal number 21, and we want to convert this guy into binary, base 2. So decimal means this guy's starting off as a base 10 number. All right, and I have to kind of tell you that because 21 is a legal number in a whole bunch of bases. All right, this is a legal number in base 3. It's a legal number in base 4, base 5, base 6. Just keep going. Okay, it's not a legal number in base 1 or base 2. So, for instance, when I say binary, base 2, what are the legal digits in base 2? 0 and 1. Okay, right? We have two different digits. 0 and 1 are the legal digits in base 2. So it's 0 to the base minus 1 are the legal digits. So octal, legal digits are 0 to 7. Decimal, base 10, our legal digits are, digits are actually the wrong. When we're dealing with decimal, digits is the right word. Okay. When we're dealing with decimal, our legal digits are 0 to 9. When we're dealing with binary, I think it's the legal, I think it's bidgets. I think it's bidgets. Huh? It's not bits. Yeah, it's each one, for octal, it's octets. Right. Yeah, but we're going to just say digits because we're still mostly human, right? All right, so okay, you get what I mean when I say digits. All right, so for base 10, our legal digits, and that is the right use of the word, is 0 to 9. 0 to the base 10 minus 1. Okay, we all know that, right? If I asked you to write one digit down, pick your favorite single digit. Not your favorite number, your favorite single digit. Your options are 0 to 9. Correct? Because 10 is 2 digits. Maybe we've gone too far then. All right, so we want to convert 21 in this case to base 2. So 21 from base 10 to base 2. So what we're going to do is we're going to take 21, we're going to divide it by 2. Okay, and this is in long division. So 2 goes into 21 10 times, right? 10 times 2 is 20, so we have a remainder of 1. Now, if I divide any number by 2, what are my possible remainders? If I'm doing long division by 2, what are my possible remainders? 0 or 1, okay? It could either go into it the exact number of times, or I might have 1 left over. Now, if I ever do long division with a 2 and I get a remainder of 2, what does that mean? I did my division wrong, right? It actually went in 1 extra time. So I could say, well, 2 goes into 21 9 times with a remainder. Oh, that's not going to work. Of 2. Well, we know that if we're dividing something by 2, you can't have a remainder of 2. If you had a remainder of 2, that actually means that, this kind of should be 1 bigger than it used to be, right? So in this case, 2 goes into 21 10 times. 10 times 2 is 20, and we have 1 left over to get us to 21. So if we were to do long division, 21 divided by 2, the answer would be 10, remainder 1. Make sense? All right, so I'm recording my quotient here and the remainder here. Then we keep going because we're going to keep doing this over and over again until our quotient finally reaches 0. So we're not 0 yet. So now we take 10 divided by 2. How many times does 2 go into 10? 5 times. 5 times 2 is 10 with remainder what? 0. 1, 2, 3, 4, 5. Yeah, close enough. All right. This guy's still not a 0. 5 divided by 2. How many times does 2 go into 5? 2 times. 2 times 2 is 4 with remainder 1. Okay. How many times does 2 go into 2? 1 time. 1 times 2 is 2 with remainder 0. How many times does 2 go into 1? 0 times. 0 times 2 is 0 with remainder 1. 0 times 2 is 0. We need 1 more to get us to the 1, so we record our remainder there. We know we're done because our quotient was finally a 0. Then we read the answer from bottom up. And it just so happens I always pick a bad example and give you something that reads the same way both directions. So the answer here is this 1 followed by this 0 followed by this 1 followed by this 0 followed by this 1. So you read it from bottom up. 1 0 1 0 1. Even though in this particular example it reads the same way forwards or backwards. All right? But you do record your answer from bottom towards the top. That makes sense? So 1 0 1 0 1 is 21 in base 2. Now let's prove that. Let's go the other direction. So we're going to conversion from a base to to decimal. So we have 1 0 1 0 1, 1 0 1 0 1, and we want to go that guy from binary to decimal. That is from base 2 to base 10. We do this a little different. A few minutes ago I mentioned that depending on which direction we're going, we either multiply or divide by the base. Okay? Now, we've actually been doing this our whole lives. We just didn't necessarily think about it. We may have way back when we first were learning numbers. But for right now, I'm going to spread these out a little bit. So I'm going to say 1. Oh my gosh, come on. All right, so there's my number. The reason I've spread it out a little bit is I'm going to write some other numbers underneath it. Okay? We start at the far right-hand side. This guy is always in the ones place. Now, as I move to the left, I multiply this value by the base. So this guy is in the twos place. It's really dumb that it wants to put periods after everything. Let me actually just go back to the beginning here. So this guy's the 16s place. This guy's the 8s place. This guy's the 4s place. Whatever. All right. So this is the 1s place, the 2s place, the 4s place, the 8s place, the 16s place. So then what we do is we just multiply and add everything up. So we take 1 times 1 plus 2 times 0 plus 4 times 1 plus 8 times 0 plus 16 times 1. So in this case, we could ignore anything with zeros, right? So this is actually 1 plus 4, which is 5, plus 16, which is 21. Make sense? So 1 plus 0 plus 4 plus 0 plus 16 gives us a 21. Now, I said we've been doing this our whole life because what if I said I want to convert 21 from base 10 to base 10? So here's our 2. There's our 1. This is the 10s place. This is the 1s place. So we have 1 times 1 plus 2 times 10, which is equal to 21. Kind of a waste of time to convert from base 10 to base 10, because we already had it. But we see that the math works identically, right? Same exact thing. We've been doing this our whole life. We just have forgotten that when we deal with our numbers and I say something is 21, that we have 1 1s and we have 2 10s. That is 21. That has a value to us. But we're so used to working with numbers until they get to some gigantic size that starts making us uncomfortable, right? So for most people, we got the 1s down, so we can deal with 1 to 9 or 0 to 9. Okay? We got 10s down. We got hundreds down, and thousands we're usually pretty good with. Hundreds of thousands, tens of thousands we're good with. Once you start getting up right around 1 million plus, that's when we start losing track of the zeros and that kind of stuff, right? We have to at least think about it. So maybe 1 million and 1 billion where we can work with, but we can't just glance at it and say that's 1 billion or 1 million. We have to do the counting of the zeros thing, right? Or do the groupings. Okay, but after we get past 1 billion or 1 trillion, then we start not knowing the names of them, right? Quadrillion and quintillion and septillion and all those sestillion and septillion and so on and so forth, right? So because those aren't numbers we're used to working with, right? On a daily basis, while we might wish that our bank account had a number in the quadrillions, chances are it's significantly south of that. Right? Even Bill Gates is. Okay, Bill Gates, what is he worth right now? Like 68 billion or something. So you only need to handle billions in order to be the richest person in the world. So that's dealing with our bank account. Now, age, every now and then we clear 100, right? So we're okay with that. 10 fingers, 10 toes, that's easy. Number of miles, if you're driving somewhere, what's a really, really, really long trip? 1,500 miles or something like that, So in a daily basis, the numbers we actually have to deal with are, relatively small compared to how big we know numbers. Well, numbers go in infinity, but in terms of what we have names for, okay, we eventually run out of stuff. So conversion between bases is always the same. Make sense? All right, so let's test this. So take about 3 or 4 minutes, and let's convert. We'll use our first example. Okay, so we're going to convert a decimal number to some other base. All right, so let's convert the number 1,000. Actually, let's make it a little bit shorter. That way it's so let's do 271 from base 10 to base 3. Okay. 271 from base 10 to base 3. Now, what are the legal, I'm guessing it's trijets in base 3? It's going to be 0, 1, or 2. So when we divide anything by 3, the possible remainders are 0, 1, or 2. All right, so take about 4 minutes. Go ahead and do this conversion. 271 from base 10 to base 3. I'll pause the recording. Okay, we'll flip through single pages of our responses here. That was my example. This was your example, right? And then this was your example as well. So there we've now it's back on the video. All right. So we're going 2989 from base 10 to base 16. So 2989 divided by 16 is 186. 186 times 16 gives me 2976. So 2976 has a remainder of, what is it? 13? Okay. 186 divided by 16. Divided by 16 is 11. 11 times 16 is 176. So that's a remainder of 10. $16 goes into 11. How many times? 0 times. 0 times 16 is 16 with remainder 11. So our previous protocol would have said, oh, we read our answer from bottom up. So this is 11, 10, 13. So it must be 111013. That would be a common mistake. Doesn't work that way. We need to convert these guys to their equivalent hextets. So this is a B. This is an A. This is a D. So this is actually the hexadecimal value BAD. Favorite. Go ahead.
Are those like universally known?
Yes. Yeah. 10 is always an A in hexadecimal. 11 is always a B in hexadecimal, which then becomes an interesting thing. The maximum base that we can represent using the English alphabet is base 37, right? We can't go any bigger than that. Okay, so without making up symbols, and then we got to start. I think it's 36, base 36.
What if we swap bases?
Well, okay, but no, you're right. We could, and then but generally hexadecimal. It is base 37. Yeah, base 37. Generally hexadecimal interchanges lower and upper and lowercase. Standard is typically uppercase, but you'll almost always. So if you're doing, if a mathematician was doing this, they'll almost always represent hexadecimal numbers as uppercase characters. But usually when you print out a memory address on a computer, it's almost always lowercase. Kind of interesting. So because of the standard, we can't go there. A student last semester, I think, suggested Klingon. We looked it up. I think there's only like 22 characters in the Klingon alphabet, so that's not going to swing. Punchline is the standard because we used to use ASCII, American Standard Code for Information Interchange, which only has 256 unique characters and is focused on the English alphabet. Our world standard for conversion stuff uses the English alphabet. So we are stuck with the number of characters in the English alphabet. Now, having said that, if we absolutely needed to have a bigger base, a bigger conversion, convert to base 700, okay, we could certainly make up a series of symbols or something like that and call that the new standard for data representation, right? I mean, the letters we use are relatively unimportant other than the fact that we've accepted it as a standard for data representation, correct? If I give you a $5 bill, it's just a piece of paper with a 5 written on it, okay? We've accepted that guy is actually a $5 bill because it's become a standard here in the country. Make some sense? So if push came to shove, we certainly could introduce a new standard to make this happen. Now, having said that, so first of all, do we get the thing here, BAD? And if we went back the other direction, if I said BAD from base 16 to base 10, we would do the other pattern where we have B, A, D, and this is the 116s, this is 256 place, this is the 16s place, this is the 1s place, so we do the math, this is 11 times 256 plus 10 times 16 plus 1 times 13, and this should give us 2981. So that's going back the other direction. So now the question would be, why would we use base 16? So I've kind of showed you an example that our computer memory addresses are typically represented as base 16 numbers. Why? Why not base 10? Or why not base 2? If we say computers like binary so much, they're digital. What do you think?
It makes it easier for the computer. Just ones and zeros.
Okay, well, your ones and zeros would make it easiest for the computer, but I'm telling you, memory addresses are represented as hexadecimal. So what we're going to do, and I'll go ahead and put this on Slack, and then I'll put it up on Blackboard. So write a 2 to 3 page paper discussing the role of binary, octal, and hexadecimal in modern computing systems. So basically, I want to know, when is binary used, when is octal used, when is hexadecimal used, and why? Why do we have 3 different bases that are used on the computer for different purposes? So, next class, we want to look at the punchline. That make some sense? All right, I will see everybody on Friday. So I'll put this up on Blackboard.